Hi everybody, this is section 4.4, other common functions from our Hawkes Learning College Algebra textbook. So again, earlier in the last section we talked about linear and quadratic functions. So now we are going to look at the graphs as the exponent increases. So like a cubed or an equation to the fourth root and then beyond. And we're really going to have two categories when we consider these functions, the behavior of the functions. And really it's going to fall into two categories, whether your exponent is odd or even. So the first one we're going to look at, I want you to take a look at these graphs and notice that we have a linear equation here where x is to the first power, x to the third power, or cubed root, and then x to the fifth power. And look at the three equations. What you'll notice about each of these graphs is that each graph basically like spans the whole grid or the whole graph. It doesn't miss out on, going from the negatives on the x and the y values to the positives on the x and the y value. And really what this means is if you have an odd exponent, so the first power, the third power, the fifth power, seventh power, your domain, which again, remember, is your x values, and your range, which are your y values, are both going to be the entire set of real numbers. So that means like the domain and the range, when they ask you for them and you write them, your domain would be negative infinity to positive infinity, and the range would be the same. So with an odd graph, I always just think like it covers the whole graph, and you'll see the difference between that and an even exponent in a second. So here we have the even function graphs, and we have like here we have a parabola with our x squared. We have x to the fourth power, which is very similar in parabola shape. It flattens a little on the bottom. X to the sixth power. So here, when you have an exponent that is an even natural number, your domain, so the x values are always the set of real numbers. So the domain is always going to be, just like it was before, negative infinity to positive infinity. But your range is going to be start at 0 and go on to positive infinity. Because if you notice, there's nothing down here. And there's nothing down here. And again, these are just equations where you have a number times x to the second or the fourth power or the fifth power. That's what your range is going to be. All right, now we're going to look at the graphs of these two equations. We have the first one, f of x equals x to the fourth power divided by 5. And this equation, we have x to the fourth power and our a value here. You may say, well, there's nothing next to the x to the fourth power. But remember, x to the fourth power is the same as 1/5 times x to the fourth power. So our a is 1/5 times x to the fourth power. It's an even exponent. So is it going to cover half of the graph or the whole graph? And in this case, since it's even, you should have said it's going to be on that upper half. And we're going to take a look at the equation in a minute. Then we have g of x equals negative x cubed. We have an odd exponent. So this one is going to cover more of the graph. It's going to cover the whole graph. All right, and here is our graph for our, I think it was f of x. I can't remember. Yeah, it was f of x. So here's our f of x equals, and again, I changed it to 1/5 x to the fourth. It's easier to look at, I think. But here's the graph. It opens up because this is a positive a value. And it is, they sketched it out again. I would expect you guys to sketch it on a calculator. not necessarily graph it. They might ask you to find an ordered pair or two, which then, plug in a value for x to find the y value. Remember, this is f of x is the same as y, and then plot those ordered pairs. But domain, all real numbers, because I can pick any number on the x-axis and find a y value. Because remember, this graph, it goes out and it's going to keep, and I'm stretching it before it should be, but it's going to keep going up. So, if x is -6, my y value may be a little bit higher, but it's going to be somewhere up here. But the y, on the y-axis, it starts at 0. There is nothing on the y-axis down here. If I put in a -2, I'm going to get an expression that's undefined. I'm not going to be able to find a value. All right, so here is our g of x. And it was -x to the 3rd power, I believe. So here is a picture of the graph. And again, your graph, it spans, like I said, through the whole top and bottom of the graph, I guess. And so your domain and range would both be all real numbers. And if they asked you to plot a few points, again, pick an x value. So like if we were to graph it, I can pick, -1. And then what I would do is put in -1. Let me erase that a little bit. So I'd put my -1 there and cube it and then take the opposite. So -1 cubed is -1. And then when I do the opposite of that, it gives me a +1. So there's our 1 point. And then you could plug in 1 or a different point, just a couple points to graph. If they ask you to graph it, which they may do on Hawks, they ask you to plug in a couple points and then they sketch the graph. But again, I really want you to be able to read the graph, look at the graph. Is it an odd exponent or an even exponent based on the shape and where the graph is located? All right, so the next type of functions we're going to look at are functions where they're in the form of a divided by x to the n power. Or this is the same as having a negative exponent. So when you have a negative exponent, a has to be a real number, n has to be a natural number, so like 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to look at how the graphs would look. And again, it's going to depend on, is the graph even, or the exponent, even or odd. And we're going to look at those two different types of graph in the next couple slides. All right, so when your exponent is a negative, or they've turned it into a positive by taking the reciprocal, then your graph, before, like when we had x cubed, and again, I'm not very good at sketching, but it looked something like this. Now, if you notice, we don't have that anymore. It actually splits it into 2 quadrants or 2 separate graphs. And that happens to be the same for 1 over x or 1 over x cubed or 1 over x to the 5th power. If your exponent is even, it still does the same thing. But what happens now is it splits the graph into, it still splits it into 2, but now, again, remember with the even functions, they were all up above the x-axis. The same thing if you had a negative exponent, or it's an even exponent, so 1 over x squared, 1 over x to the 4th, 1 over x to the 6th. It still splits it, but it's all above that x-axis. And it won't cross over the x-axis to the... So now I'm sure one of the biggest questions you have is, well, what is the domain for those crazy equations? If you have a domain of a over x to the nth power, your domain is going to be -infinity to 0, but it doesn't include 0, so you have to put parentheses around it. Parentheses around 0, and then infinity. So it basically includes everything but 0. The range is a little bit different. The domain is the same if it's odd or even functioned, but the range, if it's an odd function, your range is the same as your domain, everything but 0. But if it's an even function, now instead of it including 0 and going on to infinity, it starts right after 0. So it's 0 to positive infinity. Okay, so the next type of graph that we're going to look at is now if we have an equation where our exponent is now going to be a fraction. So like 1/2, 1/3, 1/4. And it's like a square root, a cube root function, because when the exponent is a fraction, you can turn it into a radical. So we're going to take a look at those graphs on the next slide. Okay, I lied. We're going to look at the domain and the range first, then we're going to look at the graphs. So the domain and the range. When your exponent or your denominator is odd in that exponent, the domain and the range are the entire set of real numbers. So again, that would be negative infinity to positive infinity. And the domain and the range when your exponent denominator is even will be 0 to positive infinity. And because you have the bracket around the 0, it means that it includes 0 and goes to infinity. Okay, so again, here are our graphs. When our exponent is a fraction, or like 1/3, 1/5, 1/1, it's still going to be a linear equation, so that didn't really change. This didn't really change much. But here, you'll notice, again, the graph is turned on its side, but it still spans the entire length of that x-axis, and as it goes down or it goes out, it goes up, so it would span the entire y-axis. So again, it's all real numbers for both. And then here, for the even equations, you notice that it starts at the origin, and then it goes up and out. So again, there are no negative values for x, and there are no negative values for y. So that's why the domain and the range are both 0 to positive infinity. Okay, so now what we are looking at is the next type of function we're going to look at is the absolute value function. The absolute value function is f of x equals, again, the absolute value of x. And it works for any value of x. F of x is a non-negative, which means y can't be negative, because again, if you're taking the absolute value of something, it's always going to be positive. You have no negative distances. So the graph should lie on or above the x-axis. And again, the definition of x absolute value equals whatever's inside the symbols if x is greater than 0. If x is a negative number, so if it's the opposite of x, or it's opposite, it's a negative number here, x is going to be less than 0. But we're not worried about that. All right, so here is your absolute value graph, your typical one. And again, your domain, if you look at it, because it goes out and up, your domain would be all real numbers, or negative infinity to positive infinity. Your range starts at 0 for the y value. There's no negatives, so it would be 0 to positive infinity, because again, going up this line, we have values that we can make with the x values. All right, the last type of graph that we're going to talk about, or function, is a piecewise function. And a piecewise function is, kind of think of it like a piecewise quilt. It's made up of all different types of material or shapes or sizes. A piecewise function is defined in 2 or more formulas, and then each formula is valid with its own unique portion of the number line, so it has conditions where it works and where it doesn't. And you have to make sure when you're evaluating your piecewise function that you're using the correct values to substitute in for x. Okay, so here we have an example of a piecewise function, and we have 2 equations. The first one is x, negative 2x minus 2. So again, this is a linear equation. And this function works if x is less than or equal to negative 1. So what that means is for any value that you plug in for x, it has to be less than or equal to negative 1. So I can plug in negative 1, negative 2, negative 3, negative 3.5. I can't, it's undefined or it doesn't exist if I plug in values greater than negative 1. The second part of our graph is x squared, so it would be parabola. In our case, the function exists if x is greater than negative 1. So again, when I'm trying to find x values to graph this, I have to plug in numbers that are greater than negative 1. And we're going to take a look at the graph in a second, what it is saying down here. Like if we go to sketch it, we're actually going to have two different parts of a graph. The parabola will not be the whole parabola, and the line won't be a whole line because it'll have a stopping point or a starting point. So again, the function is a linear function from the interval of negative infinity to negative 1, and it's a quadratic function from negative 1 to infinity. So you're going to have two different portions of your graph. We're going to take a look at the complete graph in a minute, and like they did points negative 4 equals 6 and 2 equals 4. Now, what's important with these 2 points is f of negative 4 equals 6. That negative 4 will only work into one of these 2 equations. Which one does it fit into? Hopefully, you're thinking, well, that number is less than or equal to negative 1. So in order for them to get the 6, they plugged it into the negative 2x minus 2 because the negative 4 meets that requirement. So they did negative 2 times negative 4 minus 2. Negative 2 times negative 4 will give me 8. 8 minus 2 will give me 6. So that's how they got the answer there. F of 2 equals 4. 2, all right, is a number that's greater than negative 1. So when I go to plug this one into one of my 2 equations, I have to choose the x squared because that's where it fits in the inequality. So now that means if I did f of 2, it would be 2 to the second power, which gives us our 4. Okay, so you're going to see here they graphed the 2 equations. Here is our the straight line, obviously, is our negative 2x minus 2. And when you're graphing the piecewise functions, which you guys don't do a lot of, I don't believe, but when you're graphing it, what you want to do is whatever is your stopping or starting point in your inequality. So before it was for the negative 2x minus 2, it was x is less than or equal to negative 1. So negative 1 is your starting point. So when you're finding points to graph, you always want to put that negative 1 in there. So I would evaluate it, and I would do negative 2 times negative 1 minus 2. So that's going to give me 2 minus 2 and give me a 0. So that is the starting point for my equation. And you'll notice we put an open circle here because we include negative 1 on that. And then our other point was when we plugged in the other value, which I think was negative 4. And that was our negative 4, 6. Then we could draw our line. Again, the line does not extend out past this point because that does not fit in our domain. So we wouldn't put that there. All right. For the quadratic portion, the f of x equals x squared. Again, the requirement there was x has to be greater than negative 1. So that means it doesn't include negative 1, but it starts right after it. But when you go to graph it and put some ordered pairs in, you do need to put that negative 1 value in there and evaluate it. So we would do f of negative 1. We'll do f of negative 1 equals negative 1 squared. So that would give me negative 1 squared is 1. So my ordered pair would be negative 1, because what I plugged in for x, 1. And again, with the open and closed dots, if you notice right here, they put an open dot because it doesn't include -1, but it starts right after that. And then they sketched in their other point that we found on the other page, and they just sketched the parabola. And that's what you guys would do. I wouldn't expect like a perfect parabola, but you need another point and kind of, it's going to be parabola shaped. So you kind of just sketch in that parabola. You can find the vertex if you want. You don't have to, unless they ask for it. But so that is it for section 4.3. Hopefully, really most of it in this section is just I want you to get used to looking at the graphs, identifying if it's an odd or an even exponent, or if it's a fraction for an exponent, or it was a negative exponent, absolute value equation. Just knowing those types of equations, because in the future sections, we're going to look at more advanced equations and like what happens if it like stretches or shrinks, or is it a reflection of the equation? So like just looking at how we can modify graphs or parent functions as they're called, which is what we looked at here. All right, have a good day, guys. I will talk to you later.